Hello, another static electricity video. This time, what I'm going to be talking about is the conservation of charge. Suppose we have two metal balls and they both have a charge. I'm going to say there's +6 on this one and -10 on this one. So we've got extra positives here, or a lack of negative charges, and then we've got extra negatives here. What's going to happen if I touch these two balls together? So I put them in contact with each other. All right, well, something's going to happen, right? They're not just going to say 6 and -10. So what would we end up with if we touch them together and then we separate them again? All right, so that's what this is about. Now, there's something called the conservation of charge. This idea is simply that we cannot create or destroy charge. We can't create an electron, we can't destroy an electron, we can't create a proton out of thin air, we can't destroy one. And so the total number of charges that we have in a situation has to stay the same. That's the conservation of charge. To solve something like this, we're going to think about the way that the charges act, and I'm going to give you two different ways to model it. And this is, again, modeling. We know in the physical world that only the electrons move, but for some people, the model helps if you think about what the positives are doing and what the negatives are doing. So you can keep that in mind. This is just a model, but it does often help to have people think about this in terms of positives and negatives moving. So if I have a +6 and a -10, okay, I'm going to do this in terms of charges. Let's do this. So I have 6 positives on this, and I have 10 negatives. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if these are metal balls, they're spread out evenly over those metal balls because all these positives are repelling each other. All the negatives are repelling each other. And now I'm going to bring them in contact. So when I bring these two metal balls in contact with each other, contact means the charges can move back and forth. So if we have those 6 positives, they're repelling each other, and now I've given them more space to hang out in. They say, oh, I can spread out a little more. They repel each other and spread out evenly across now those two surfaces, those two metal balls. So the positives are going to do that. Negatives are going to do the same thing. So I'm going to end up with 5 on here, 5 on here. And so they're spreading out evenly across the two balls. So now I separate the two metal balls, and what do I have? I have 3 positives here and 5 negatives. +3 and a -5. So +3 -5, just do the math really. That would give me a -2 here. Same thing here, -2. Okay, so what I'm saying is if I take a +6 and a -10, I take them, touch them together and separate them, they both end up with a -2 charge. And here's where the conservation of charge comes in. We had better have the same total amount of charge at the beginning as at the end. What was our total amount of charge here? Well, the total amount of charge, I had +6 and -10. I have a total charge of -4 to start with. I'd better have -4 at the end. Do I have -4? Yes, I have -2 and -4. -2 and -2, giving me -4. Wow, I misspelled that. I miswrote that and misspoke it. That was a good one. -2 and -2 gives me a total of -4. There we go. So this is the idea of conservation of charge. However much charge, total charge you started with has to be the same as the total charge you end with. And that leads us to the other way to solve these problems. So you can think about it in terms of the positives and negatives, what they're doing, and then add them up. You can also say, well, how much charge do I have at the beginning? I have -4. If these are two identical balls, if they have the same size, then the charges are going to spread out evenly across those two. So I can take the total charge, divide it by 2, and I'm going to end up with -2. So you can kind of jump from this math right here, divide each 2, or divide it evenly across the 2 metal balls, and then you've got your -2. So that would be another way to do it. So if I had, let's see if I can do the math real quick. Should have come up with something to do beforehand instead of doing this off the top of my head right now. A -6, a -10, and let's do a -2, I guess. So what would we have if we touched all these 3 together and then separated them out again? So the easy way to do this is just to say, again, what's my total charge? I have a a +6. I have a -10, and now I have a -2. What does that add up to? That gives me a total of -6 charge. I'm going to say that if all 3 of these are equal sizes, that -6 charge is going to be distributed evenly across all 3. 6 split 3 ways is going to give me, again, should have used different numbers, but it works, -2 on each. And so this is just an example of conservation of charge and how we can use that to figure out when we are touching 2 objects together with different amounts of charge, what's happening? How do the charges spread out, move around? What do they end up with if we have this contact between 2 charged objects? So there's yet another static electricity video. Good job for watching.